Okay, so in this video, we're going to talk about some exact differential equation, how to determine whether a differential equation is exact or non-exact, and basically how to solve the general solution of an exact differential equation. But before that, let's formally define what's an exact differential equation is. And you know that the equation m of xy dx plus n of xy dy equals 0 is an exact differential equation if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Okay, so let's verify whether this differential equation is exact or non-exact. Say we have 2xy plus x cubed dx plus x squared plus y squared dy equals 0. So here, obviously, you have m is equal to 2xy plus x cubed and n is equal to x squared, yeah, plus y squared. Okay, and then we are going to differentiate m partially with respect to y. And again, when you're differentiating a function with respect to y, you hold other variable constant. So when you differentiate 2xy with respect to y, so you just copy 2x and then you just differentiate y, and that is 1, plus since this x cubed does not contain any y, then its derivative is 0. Okay, so meaning the partial derivative of m with respect to y is equal to 2x. Then for n, we shall differentiate this partially with respect to x. So when you are differentiating with respect to x, you are holding y constant. So x squared, the derivative is 2x by power formula, and the derivative of y squared with respect to x is 0. So therefore, the partial derivative of n with respect to x is equal to 2x, and you notice that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, and therefore this equation is an exact differential equation. Okay, example number 2, say we have 2xy minus tangent y dx plus the quantity x squared minus x secant squared y dy equals 0. Again, we can write m equals 2xy minus tangent y, and n is equal to x squared minus x secant squared y. Right? So then we shall differentiate m partially with respect to y, again holding x constant. So which means you just copy 2x, right? And then you differentiate y, and that is 1. And you take the derivative of negative tangent y, and that is negative secant squared y. So you have 2x minus secant squared y. And then for n, you differentiate this partially with respect to x. So this is x squared. With respect to x, the derivative is 2x. And since you are differentiating with respect to x, you just copy secant squared y, okay? And then you differentiate x, and that is 1. So you have 2x minus secant squared y. And obviously, the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And therefore, this equation is an exact differential equation. Okay, and to look for the solutions of an exact differential equation, then we just follow the simple step. Number 1, we let m be equal to the partial derivative of f with respect to x, and we let it to be equation 1, and n is equal to, let it be the partial derivative of f with respect to y, and let it be equation 2. Okay, step 2, you integrate equation 1, so we will be integrating this df dx, okay, partially with respect to x, and then that means you're taking y constant and letting it to be equation 3. Then step 2, or step 3, sorry, differentiate equation 3. So whatever the result you obtained in step 2, you differentiate it partially with respect to y. That means you're taking x constant and setting the equation or the result be the equation 4. Okay. Then step 4, you equate equation 4 and equation 2. So this, you equate it to the result of step 3 and let it be equation 5. And then step 5, integrate equation 5 and let the result be equation 6. And finally, step 6, you substitute equation 6 to equation 3, and then you set capital F equals C. Okay. So example number 1, say we have already verified that this DE is an exact differential equation. So step 1, okay, we let M be equal to the partial derivative of f with respect to x, and n the partial derivative of f with respect to y. So we shall have df dx is 2xy, this 2xy plus x cubed, all right, and let it be equation 1. And then the partial derivative of f with respect to y, so that's x squared plus y squared, okay? And that let it be equation 2. Step 2, integrate equation 1 partially with respect to x, taking y constant, and let the result be equation 3. So we are integrating the partial derivative of f with respect to x, okay? And you are integrating 2xy plus x cubed with respect to x. So x. You know that the integral of the derivative of f with respect to x is simply f or fx, yeah? And equals, since you are differentiating with respect to x, then 2y will be treated constant. You can just throw it out. So that's 2y, okay? And then you integrate x, and that will be x squared over 2, okay? Plus, you take the integral of x cubed dx, so that's x to the 4 over 4. So we're not going to add c. Instead, we are going to write h of y plus h of y. So we have f is equal to 2x squared y all over 2 plus 1/4 x to the 4 plus h of y, or you can just simplify this as x squared y, yeah, you can drop this off, x squared y plus 1/4 x to the 4 plus hy. Okay, step 3. We shall now differentiate equation 3. So we will be differentiating this with respect to y, okay? So we're going to take x constant and let the result be equal to equation 4. So we shall differentiate f, and you will differentiate this x squared plus y plus 1/4 x to the 4 plus hy partially with respect to y. So you know that the derivative of f with respect to y is the partial derivative of f with respect to y equals, we are differentiating with respect to y, we are going to treat x constant. So you just copy x squared, and then you differentiate y, and that is 1, plus, since we are differentiating with respect to y, since there's no y here, okay, then the derivative of 1/4 x to the 4 is 0, plus the derivative of hy in terms of y is h prime of y. Okay, so we have the partial derivative of f with respect to y is x squared plus h prime of y. Okay, and then step 4, equate equation 4. So this equation 4, so that's x squared plus h prime of y equals, equation 2 is x squared plus y squared. Okay, and then you simplify. So you can take this out. So when added, that will become 0, meaning h prime of y is equal to y squared. Right? So that is our x squared plus y squared equals x squared plus h prime of y. And then you'll have y squared equals h prime of y. And then step number 5, we shall integrate equation 5 and let the result be equation 6. So we shall integrate y squared dy equals integral of h prime of y dy. All right? So we shall have y cubed all over 3 equals h of y. And then we shall have, yeah, 1/3 y cubed equals h of y. So then step 6, substitute equation 6 to equation 3. Okay, remember our equation 3 and set capital F equals c. Remember our equation 3 is f equals x squared y plus 1/4 x to the 4 plus hy, and then we shall replace this hy by 1/3 y cubed, and then this f by c, and eventually we arrive at our final answer. Okay, so we replace hy by 1/3 y cubed, and then we shall replace this by c. So we have C is equal to x squared y plus 1/4 x to the 4 plus 1/3 y cubed. And that's the general solution of this differential equation. Okay, let's try another method on how to solve this differential equation. And this method is you're just going to get the sum of the direct integrable plus the non-direct integrable. Okay, so that's the summation of the integral of the direct integrable plus the integral of the non-direct integrable, and that is equal to C. So what do you mean by direct integrable? So those are the functions f of x dx and f of y dy. Okay, and the non-direct integrable, those are the function containing f of xy dx and f of xy dy. So when you look at the given and you introduce dx each term, dy each term, you shall have 2xy dx plus x cubed dx plus x squared dy, all right, plus y squared dy. When you try to see this function, so this is f of xy dx, since there's an x and y here. So since this is x cubed alone, so this is your f of x dx, plus since this is x squared and it go along with dy, we can write it as f of xy dy, plus, and since this is y squared alone, so this is your f of y dy. So we can now say that this is non-direct integrable because it contains f of xy, and this is direct integrable, this is non-direct integrable, and this is direct integrable. All right, for our first example, okay, that's 2xy dx plus x cubed dx plus x squared dy plus y squared dy equals 0. Okay, and then the direct integrable are x cubed dx, this one, and y squared dy. Okay, and the non-direct integrable are 2xy dx, this, or x squared dy. Okay, so what are we going to do is we just get the summation of the integral of the direct integrable. So that's the integral of x cubed dx plus the integral of y squared dy. And for the non-direct integrable, you just only choose between these two. Okay, say you want to use 2xy dx, or you can also use x squared dy. Say plus the integral of x squared dy. Okay, equals the constant c. Okay, so we have, this is the direct integrable, and here I choose 2xy dx. So here I will be using x squared dy. Okay, so we just only choose one of the non-direct integrable. All right, so you know that the derivative of x cubed dx is x to the 4 all over 4, plus you know that the derivative of y squared dy is y cubed over 3, plus since you are integrating 2xy with respect to x, so you treat 2y constant, so that's 2y, and then you integrate x dx, so that's x squared all over 2 equals c. So you shall have x to the 4, or 1/4 x to the 4 plus 1/3 x, or y cubed, sorry, that's 1/3 y cubed. And then you just cancel this out, so you have x squared y plus x squared y equals c. Okay, so you shall have this, and so that's 1/4 x to the 4 plus 1/3 y cubed plus x squared y equals c. And I think this is similar to the result in solution number 1. Okay, or you can use this x squared dy, so you shall have, this is the direct integrable, and you just pick x squared dy, so that's the integral of x squared dy partially, and that's equal to c. Okay, so again, you know that the integral of x cubed dx is x to the 4 over 4, plus the integral of y squared dy is y cubed over 3, plus since this is constant, x squared, and then integrate dy equals c, and you know that the integral of dy is y, All right. So you shall have x to the 4 over 4 plus y cubed over 3 equals the constant c. Yeah, and I think we got the same answer. So that's x to the 4 over 4. That's 1/4 x to the 4. Then 1/3 y cubed. So 1/3 y cubed plus x squared y. Then this is x squared y and then equals c. Okay. Another one. Say 2xy minus tangent y dx plus x squared minus x secant squared y dy equals 0. And earlier, we have seen that this is an exact differential equation. Okay? Okay, and then step 1, we let the partial derivative of f with respect to y be equal to 2x minus secant or 2xy minus tangent y, this m. All right. And then df dy is x squared minus x secant squared y dy. All right. And then step 2, we integrate df dx partially. So equals the integral of 2xy minus tangent y dx. Since you are integrating with respect to x, okay, since we are integrating with respect to x, we will be treating y constant. So you shall have 2y integral of x dx, then minus, since tangent y is constant, you can throw it out, tangent y integral of dx. And then you shall have 2y, then this is x squared over 2, that's the integral of x dx, minus tangent y, and the integral of dx is x. Then plus h of y. Then you have this. Okay? So that's 2x squared over 2x squared y over 2 minus x tangent y plus h of y. Okay, and that is our equation 3. Then step 3, we shall differentiate this f. So we shall now differentiate this with respect to y. Partial derivative of f with respect to y. So we shall have df dy equals, again, differentiating this with respect to y. So you got x squared, that's constant. Then derivative of y is 1. So with respect to y, this negative x is constant. And then you know that the derivative of tangent y is secant squared y plus h prime of y. And then you have this. The partial derivative of y or f with respect to y is equal to x squared minus x secant squared y plus h prime of y. And let it be equation 4. And then step 4, okay, we shall equate equation 4 and equation 2. All right. So you shall have x squared minus x secant squared y plus h prime of y equals this x squared minus x secant squared y. And then we combine. So this will become 0. And this is also 0. And eventually you only have h prime of y equals 0. Okay, and that is our equation 5. Step 5, we shall integrate this with respect to y. So you know that the integral of h prime of y is h of y equals c. And then step 6, okay, we shall substitute this to equation 3. So you have f and then setting f equals c. All right. So you shall have f equals x squared y minus x tangent y. And then this hy is equal to c plus c. And then we shall replace this by another constant. I'll just let this to be c1. Okay. And then this f shall be replaced by c, a constant. And you know that c plus another constant is still another constant. And that's equal to x squared y minus x tangent of y. And that is that's the general solution that we are looking for. Okay. So that's x squared y minus x tangent y equals c. And then if you want to do method number 2, that's the summation of the integral of the direct integrable plus the integral of the non-direct integrable. So you shall distribute this dx, each term inside, to determine which one is the direct integrable and which one is the non-direct integrable. So you shall have 2xy dx, tangent y dx, x squared dy, x secant squared y dy. And you will observe that this is, this is xy. Yeah, you're correct. That's the non-direct integrable. This is tangent y and it go along with dx. So this is non-direct integrable. X squared and it go along with dy. This is another non-direct integrable. This is x. This is secant squared y. Sorry. And that go along with dy. So this is also a non-direct integrable. So obviously, there is no direct integrable. All right. So then there's no direct integrable. And for the non-direct integrable, so that is 2xy minus tangent y dx, or x squared minus x secant squared y dy. So applying the formula, we shall have, so we do not have any non-direct integrable and we only choose between these two. Okay. So you can choose this 2xy, integral of 2xy minus tangent y and then dx. Okay. Integrating this, or is equal to c. Integrating this with respect to x, to y is constant, and then you integrate x, so that's x squared over 2 minus, this is tangent y, you can just throw it out, and then you affix x, and then equals c. So finally, you have x squared y minus x tangent y equals c. And that's the general solution that we are looking for, right? So that's x squared y minus x tangent y equals c. Or if you want to use this term for the non-direct integrable, so you have integral of x squared minus x secant squared y then dy. Okay, so you have integral of, this is constant, so x squared then dy minus x is constant, you throw it out, integral of secant squared y dy. Then x squared, you know that the integral of dy is y, so you have x squared y minus x, you know that the integral of secant squared y is tangent y, and then you just equate it to c. Okay, so you have x squared y minus x tangent y equals c, and we get the same answer. Okay, sample 3. Say you have 1 plus e to the y dx plus 2x e to the y dy equals 0. Okay, so we determine whether this is exact or non-exact. So we have m is equal to 1 plus e to the 2y, sorry. And then we shall differentiate this partially with respect to y, and that is derivative of 1 is 0, then e to the 2y, that's 2e to the 2y, okay? And then n is equal to 2x e to the 2y, and then we shall differentiate this partially with respect to x. So 2e to the 2y is constant, so 2e to the 2y, and derivative of x is 1. So I think we got the partial derivative of y of m with respect to y is equal to the partial derivative of n with respect to x. So therefore, this is an exact differential equation. Okay. All right. So we proceed with the solution. Step 1. You let df dy or df dx equals 1 plus e to the 2y, and df dy is 2x e to the 2y. All right. Then step 2, we shall integrate the partial derivative of f with respect to x, and 1 minus e to the 2y with respect to x. Okay, so you have integral of 1 dx, then plus integral of e to the 2y dx. So you know that the integral of dx is x, plus this is constant, you can just throw it out, and then integrate dx. So you have x plus x e to the 2y, and that's equation number 3. Then I forgot to write h of y here, sorry. Okay. And then step 3, you differentiate this, okay, partially with respect to y. Okay. So that's 1 derivative of 1 plus e to the 2y x plus h prime plus hy with respect to y. Okay, we shall have df dy equals, you just copy x. Okay, so x, since that's constant, derivative of 1 is 0 plus derivative of e to the 2y with respect to y is 2e to the 2y. So you shall have x times 2e to the 2y plus h prime of y. That's why we have this. Okay, and that is our equation 4. And then step 4, we shall now equate equation 4 and equation 2, and that leads us to 2x e to the 2y plus h prime of y equals 2x e to the 2y. And then you can just add this 2. So you shall have h prime of y equals 0. And that is our equation 5. And then equation step 5, sorry, you integrate equation 5, and that's the integral of h prime of y equals integral of 0, and that is h of y equals constant. And then step 6, you just and then set f, that's f, sorry, this is f, set f equals c, and then I'll let this to be c1. Okay, so then you have this 1 plus e to the 2y times x, all right, plus hy, that is c1, equals f, and we let f to be c. So and then you combine this c and c1, and that will make another c equals 1 plus e to the 2y times x. Okay, and this is the general solution that we are looking for. Okay, or you can just introduce x each term inside, and that will lead you to c equals x plus x e raised to 2y. Okay, if you want, okay, example number 4. You have x times the quantity 3xy minus 4y cubed plus 6 dx plus x cubed minus 6x squared y minus 1 dy. So let's verify whether this is an exact differential equation. I will just first introduce x each term here. All right, and then you shall have m equals 3x squared y, that's 3xy times x, minus 4xy cubed, then plus 6x. And then you differentiate this partially with respect to y. So that's 3x squared y with respect to y, that's 3x squared, okay, minus with respect to y, this is 4 times 3, you copy x. Then 4 times 3, that's 12, then y, then you subtract 1 from 3, so 2. And you know that the derivative of 6x with respect to y is 0, so you can just ignore that part. And then for n, you have x cubed minus 6x squared y squared minus 1. Then differentiate this partially with respect to x. So you have it's x cubed with respect to x is 3x squared. With respect to x, y squared is constant, okay? And then 6, negative 6 times 2, that's negative 12. Copy x, then you subtract 1 from 2. And you know that the derivative of negative 1 is 0. And then you try to look at the partial derivative of m with respect to y and the partial derivative of n with respect to x, and I think they are equal. All right. So therefore, this equation is an exact differential equation. And then we shall only be looking for, we will be using this method. That's the summation of the integral of the direct integrable plus the summation of the non-direct integrable equals c. So we look for the non-direct integrable. Again, this is 3, hold on. This is 3x squared y minus 4xy cubed plus 6x dx. Okay, so this is non-direct, okay, and this is direct integrable because this is x alone. And then for the other term, x cubed minus 6x squared y squared minus 1, again dy. This is non-direct since this is x cubed and it go along with dy. This is also non-direct. And this is negative 1 dy, that's direct integrable. So we only have 6x dx and negative dy as direct integrable. All right. And then the remaining terms are non-direct integrable. So you have 3x squared y minus 4xy cubed dx and x cubed minus 6x squared y square dy. Okay. And then we now have the summation of the direct integrable minus the integral of dy, and then you only choose between these two. Say we choose this one. Then plus the integral of 3x squared y minus 4xy cubed, then dx. So you shall have 6x squared over 2, that's the integral of 6x dx, minus the integral of dy is y, plus you are integrating with respect to x. So 3y is constant, you can throw it out, then integrate x squared, and that is x cubed over 3, all right? Minus, you are integrating with respect to x, so 4y cubed is constant. Okay, and then integrate x, and that is x squared over 2, and then equate it to c. All right, so 6 over 2, that's 3x squared minus y plus 3, cancel it out, that's x cubed y minus 4 over 2, that's 2x squared y cubed, and that is equal to c. Okay. And then you shall have 3x squared minus y plus x cubed y minus 2x squared y cubed equals c. Okay. Or if you want to use this non-direct integrable, so we shall have, again, you copy integral of 6x dx minus the integral of dy, and then this is to be replaced by this. All right. Integral of x cubed minus 6x squared y dy equals c. And you know that the integral of this is 3x squared. So that is 6x squared over 2 minus y plus, you are integrating with respect to y, so x cubed is constant. And then you just simply affix y. Minus, you are integrating with respect to y, so 6x squared is constant. And then integrate y squared, and that is y cubed over 3, and then equal to c. Okay, and then you have 3x squared minus y plus x cubed y minus 2x squared y cubed equals c. Right? And I think we got the same answer here. Yeah. All right. Yeah, I think so. Then let's have some more. So here we have cosine x, cosine y minus cotangent x dx minus sine x sine y dy equals 0. Again, we let m equals cosine x, cosine y minus cotangent of x. And then we differentiate this partially with respect to y. So with respect to y, cosine x is constant, and then you differentiate cosine y, and that is negative sine y. Okay, since you are differentiating with respect to y, then cotangent of x is 0 plus 0. So you only have negative cosine of x sine y. And then for n, we let n equals negative sine x sine y. All right, and we shall differentiate this partially with respect to x. So that's negative, you affix the minus sign, you copy sine y, since we are differentiating with respect to x, and then you differentiate sine x, and that is cosine of x. And I think we got the same answer. So finally, you have the partial derivative of m with respect to y equals partial derivative of n with respect to x. And therefore, this is an exact differential equation. Okay, and then we use this method. So you just introduce dx each term inside. So to determine which one is the direct integrable and which one is the non-direct integrable. So you have cosine x, cosine y, dx, then minus cotangent x dx, minus sine x, sine y dy equals 0. So cosine x, cosine y that go along with dx, so this is non-direct integrable. This is cotangent x going along with dx, so that's direct integrable. Obviously, this is sine x, sine y go along with dy, non-direct integrable. So you have the direct integrable is negative cotangent of x, and the non-direct integrable are cosine of x, cosine y dx, and negative sine x, sine y dy. Then you have, to facilitate the general solution, you have integral of negative cotangent of x dx, okay? And then this is dx. And then you only choose between these two. So say I will be choosing cosine x, cosine y dx. So plus the integral of cosine x, cosine y dx equals c. And you know that the integral of, you copy the minus sign, you know that the integral of cotangent x dx is ln sine x. And then again, you are integrating with respect to x. So you have this cosine y is constant. You can throw it out. Integral of cosine x dx equals c. The negative ln of sine x, okay? Then plus cosine of y. Then you know that the integral of cosine x dx is sine x equals c. Okay, so we shall have, all right, and these are the integrals. Okay, and then I will let this c to be ln c so that we can combine these two. All right, and then you now have cosine y sine x equals ln c. Then this negative ln sine x, you try it on the other side, so you have ln sine x. And then you use the logarithmic identity. This is equal to ln c sine x. And then you have this. All right, and that's the general solution of this differential equation. Now, if you want to use this, let's see what will happen. So you have the integral of the direct integrable, it's negative cotangent of x dx, and then we will be using this one. All right, so that's minus, because of this minus, integral of sine x sine y, then dy equals c. Again, the integral of negative cotangent x is negative ln sine x, then minus, you are integrating with respect to y, you can throw this out, sine x sine y dy equals c. The negative ln sine x minus sine x, all right? And then you know that the integral of sine y dy is negative cosine of y, then equals c. Then you now have ln of sine x, then minus minus, you have plus sine x cosine of y, all right? Then I will let this c to be ln of c so that I can combine these two. So you have sine x cosine of y equals ln c plus ln of sine x. And then eventually, you will arrive at sine x cosine y equals ln of c sine x. All right, and I think we got the same answer, only that this sine x, okay, the sine x, so you can just write it as cosine y sine x equals ln of c sine x. And I think that's all.